Hello everyone, welcome to the video presentation. We are a group of 4 featuring Heng Ji-xiang, Chiu Yi-wei, Tan Yi-wei, and Tan Tao. We will be discussing how application of mathematical modeling can be applied to solve real-life optimization problems. How does a company maximize profit while working within specific constraints? Let's take a closer look. In this video, we will discuss a company, Potter Ceramics and Clay, that produces two products, mugs and plates. Each product has unique production costs, labor hours, and selling prices. The company's goal is to determine the optimal number of mugs and plates to produce daily to maximize profit. However, there are three key constraints. Only 100 labor hours are available daily. Each mug takes half an hour to produce and each plate takes 1 hour. Material availability is capped at 120 kilograms daily. Material used for a mug is 1 kilogram and a plate is 900 grams. The daily budget for production is 1,300 ringgit. Producing a mug costs 10 ringgit while a plate costs 12 ringgit. The profit for a mug is 14 ringgit and for a plate is 18 ringgit. By mathematical modeling, we define two variables. X indicates the number of mugs while Y indicates the number of plates. The objective function, which is the profit function, is 14x plus 18y. The constraints turn into the following equations. For labor hours, 0.5x plus y less or equal to 100. For material usage, x plus 0.9y less or equal to 120. For production budget, 10x plus 12y less or equal to 1,300. Lastly, the number of x and y cannot be negative. Therefore, x and y are greater or equal to 0.
Today, we will solve an optimization problem using Lagrange multipliers. The objective is to optimize a profit function fxy subject to multiple constraints. Specifically, we will examine a real-world scenario where we maximize profit in manufacturing while respecting resource limitation. Our goal is to maximize the profit function Pxy equal to 14x plus 18y, where x and y represent the quantities of two products. However, the constraint limit labor, materials, and machine hour available. For we formulate the Lagrange function by combining the objective function and the constraint, introducing multipliers lambda 1, lambda 2, and lambda 3 for each constraint. These multipliers help account for the influence of constraint on the solution. To solve the problem, we calculate the partial derivative of the Lagrange function with respect to x, y, lambda 1, lambda 2, and lambda 3. Setting this derivative to 0 gives a system of equations. We take the partial derivative out with respect to x, denote as dl over dx. To understand how x influences the function L, in equation 1, dl over dx equal to 14 minus 0.5 lambda 1 minus lambda 2 minus 10 lambda 3 equal to 0. In equation 2, dl over dy equal to 18 minus lambda 1 minus 0.9 lambda 2 minus 12 lambda 3 equal to 0. In equation 3, which is also equation constraint 1, is dl over d lambda 1 equal to 100 minus 0.5x minus y equal to 0. In equation 4, which is also equation constraint 2, is dl over d lambda 2 equal to 120 minus 0.9y minus x minus equal to 0. In equation 5, which is also equation constraint 3, is dl over d lambda 3 equal to 1300 minus 12y minus 10x equal to 0. To solve these five equations simultaneously to find the value of x, y, lambda 1, lambda 2, and lambda 3, we need to set the equation 1 is 14 minus 0.5 lambda 1 minus lambda 2 minus 10 lambda 3 equal to 0. And the equation 2 is 18 minus lambda 1 minus 0.9 lambda 2 minus 12 lambda 3 equal to 0. For the equation 3 is 100 minus 0.5 x minus y equal to 0. For the equation 4 is 120 minus 0.9 y minus x equal to 0. And the equation 5 is 1300 minus 12y minus 10x equal to 0. We first focus on solving the constraint for x and y. From the equation 3, we can rewrite to y equal to 100 minus 0.5x and define as equation 6. Then we substitute the equation 6 into the equation 4. We can calculate the value of x, which is for 54.55. While the value of x is successful to calculate, we can solve the value of y. We substitute the value of x into the equation 6, then we get the value of y, which is 72.73. After solving x and y, we calculate the value of lambda 1, lambda 2, and lambda 3. We multiply the equation 1 with 2 to make sure that the 0.5 lambda 1 become 1 lambda in equation 1. Then we can rewrite the equation 1 become lambda 1 equal to 28 minus 2 lambda 2 minus 20 lambda 3 and define as equation 7. Substitute equation 7 into equation 2, the equation become 1.1 lambda 2 plus at lambda 3 equal to 10, which can define as equation 8. We assume or test a value for lambda 3 such as lambda 3 equal to 0.5 and then substitute it into equation 8. This assumption is based on simplifying the solution and observing consistency with the problem constraint. After that, we calculate the value of lambda 2 is 5.45. To calculate the value of lambda 1, substitute the value of lambda 1 substitute the value of lambda 2 and 3 into the equation 1 and we get the value of lambda 1 which is 77.1. The solution provides us with optimal quantity of the two products and the value of the multipliers. These multipliers, lambda represent the shadow prices or the rate at which the profit increase if more of the respective resource become available. The Lagrange multiplier method helps us optimize under constraints, ensuring the best use of resources while maximizing the objective function. Thank you.
As interpreting the result from previous pages, which x is equal to 54.55 and y is equal to 72.725, are they satisfied for both three constraints? For the first constraint, which is 100 minus 0.5x minus y is equal to 0, so it is satisfied. And for second constraint, we get answer nearly to 0, which is negative 0.0025, but it is not 0, so second constraint are not satisfied. And for the third constraint, which is 1300 minus 12y minus 10x is equal to negative 118.2. So Third constraint also not satisfied. Since the second and third constraint are not satisfied, so we cannot use x equal to 54.55 and y equal to 72.725 as our number to produce product per daily. After we sketch the graph, we use many points as test point to get our maximum profit that shows in the table beside of me. The all testing points are tested as this table shown. We now can see that the maximum profit used x is equal to 24 and y is equal to 88 to get a 1920 ringgit Malaysia, and both three constraints are already satisfied. For the final result, we get that labor hour constraint as 100 hours, which fully use the time daily, and for material usage constraint is at 103.2 kg, is a bit less than 120 kg, and the budget constraint at 1296 ringgit is also a bit less than 1300 ringgit. Thus, thus, the optimal solution is to produce 24 mugs and 88 plates in order to maximize the water, ceramics and clays profit, which is 1920 ringgit.
In the conclusion, the potter ceramics and clay should produce 24 mugs and 88 plates, maximize its profit, achieving a total profit of 1920. These optimizations ensure that the potter ceramics and clay can achieve maximum profitability while maintaining sustainable operations, supporting better decision making, efficient resource allocations, and enhanced competitive positioning in the market.
Thanks for watching, and we hope you found this presentation insightful.